Dear students, you are welcome to this course of Basic Quantum Chemistry. Basic Quantum Chemistry is a course which is taught in every university as a core course of postgraduate and undergraduate syllabi. In chemistry, we do this exercise because in physical chemistry, there are many branches, all spectroscopic techniques are based on quantum chemistry. Besides this, one who does the material chemistry later on also requires a very good understanding of quantum chemistry courses. Quantum chemistry is actually the application of quantum mechanics to chemistry, and this application of quantum mechanics to chemistry is essential to understand the structure of atoms and molecules and the behavior of the electrons during the chemical reactions. Quantum mechanics is a core branch of physics, or the principles of quantum mechanics was developed around 1900. So in this course, in basic quantum chemistry, I will first talk about its origin and development, and then I will talk about that how actually the quantum mechanics came into existence. Before the quantum mechanics, Newtonian mechanics was available for dealing with the dynamics of small molecule of any object, dynamics of any object. But this Newtonian mechanics could not provide the explanation for a few experimental observations at the end of 19th century. And though the two such observations, which according to James Clerk Maxwell, when he was presenting before the British institutions, he said that almost all physics is complete except two small patches on the horizon of physics. And one of the experiments he talked about, one of the results he talked about was Michelson-Morley experiments. And another finding he talked about was the explanation for the blackbody radiation. So James Clerk Maxwell said that when these two are solved, the physics will be almost complete, and we will be in a commanding position. We know everything about the physical phenomena. But what he expected to vanish from the horizon of physics did not vanish, and the explanation for Michelson-Morley results led to a most elaborated theory of relativity, and the blackbody radiation explanation for blackbody radiation led to the development of quantum mechanics. In the discovery of the origin of quantum mechanics can be traced with the explanation of blackbody radiation. What was unknown? What was it? So we talked about blackbody radiation. What we say is that in blackbody radiation, when we plot a curve of intensity versus wavelength, we get a curve like this one, which is temperature dependent. The lowest curve is this is the temperature is lowest temperature, and this is the highest temperature. So this was the curve available, this was the experimental curve available, and an explanation for this experimental curve was not available through the principles of classical mechanics, or say the classical chemistry. When I say classical chemistry is thermodynamics, electromagnetism. Classical physics does contain thermodynamics, electromagnetism, law of equipartition of energy, and all these were used to tried to explain this blackbody radiation. All these principles were used for the blackbody radiation explanation for blackbody radiation. But what happened is that all these failed miserably, and there was no equation available in order to deal with this intensity versus wavelength curve for blackbody radiation. So the first attempt which was made in order to explain this blackbody radiation was done by Stefan-Boltzmann, and they used the principles of thermodynamics, and see, it is 1879 to 1884. it's the end of 19th century when the attempts were being made. And they said that the intensity of total radiation is proportional to fourth power of its absolute temperature. And he gave this equation, energy in intensity at that time was proportional to energy of the radiation. So energy becomes equal to sigma star T raised to the power 4, and then we say that this is equal to 4c divided by sigma T raised to power. Sigma was given as Stefan constants, and its value was determined in order to fit into the curve was 5.672 10 to the minus 8. So we can change the unit. Joule per second is the watt. So you can write either this unit or that unit, the first one or the first one or the second one. Both units are valid. Okay. So Stefan-Boltzmann tried to explain based on the principles of thermodynamics. So thermodynamics is a classical concept, not quantum mechanical concept, where we deal with the macromolecule and the first law, second law, and all those laws of thermodynamics. Okay. So this was an attempt to explain the blackbody radiation, which failed miserably. Thereafter, Wiens used classical electromagnetic theory, and he assumed that the emitting oscillators of the blackbody are of molecular dimension, and based on this he said that the lambda max which we get at a particular temperature is actually lambda max into T is a constant. So lambda max into T is a constant, and this becomes equal to this constant becomes equal to 2.8976 into 10 to the minus 3 meter Kelvin. So E lambda is equal to, and he derived another equation based on the electromagnetic theory as E lambda is equal to A lambda raised to the minus 5 exponential minus B divided by lambda T. So if you look at this equation, this tells you that the energy of the radiations emitted from the black body is proportional to fifth power of the wavelength. Okay. So and if you see, if you go for a higher temperature, then the exponential term becomes smaller and smaller, and so the exponential decrease is slower and slower. Okay. But this Wien's law was capable of giving you a very good fit to experimental curve in the low wavelength region. In the high wavelength region it failed, but in the low wavelength region it gave a good fit. So one part of the curve was explained by Wien's law, but other part of the curve could not be explained. The next attempt was made by Rayleigh-Jeans law, and he used the law of equipartition of energy, where we say that each vibrational mode possesses an average energy of equal to kT, depending upon the T, where T is the temperature, K is the Boltzmann constant. Okay. And based on the law of equipartition of energy, Rayleigh-Jeans derived an equation for the energy of the radiation emitted from the black body, and it was 8 pi kT divided by lambda raised to the power 4. So here he said that energy of the radiations emitted from the black body is inversely proportional to fourth power of the wavelength. In the previous law it was fifth power to the wavelength, in this law it was fourth power to the wavelength. Okay. And this equation fits the experimental curve in high wavelength region. So if you go for a high wavelength region, the Rayleigh-Jeans law gives a curve which tells you that the energy will keep on rising if you decrease the wavelength, and like this one. So if the wavelength energy will keep on rising, and this phenomena is called ultraviolet catastrophe. This phenomena is called ultraviolet catastrophe. Okay. So one of the law, Wien's law, was giving a good fit of experimental curve in the low wavelength region, and another Rayleigh-Jeans law gave a good fit in the high wavelength region. So this was already known when Planck opted for theoretical physics as his career. After finishing his study, Planck wrote to his one of the teacher, Philippe Joly, and he asked him that he want to pursue his career in theoretical physics. And Philippe Joly promptly replied that, young man, why do you want to ruin your career? because the realm of theoretical physics is almost over. I said you about the James Clerk Maxwell that at that time, at the end of 19th century, this was the feeling that physics is complete. So Maxwell also said the same thing, and Philip Joly also replied to the Plancks in the same language, that third realm of theoretical physics is almost over. Every equation has been solved, and you will be ruining your career by opting a theoretical physics which does not hold any future prospect. Even after this advice, Planck opted for this area, and he tried to solve the black body radiation problem. And he was already knowing that Wien's law fits into the low wavelength region and Rayleigh-Jeans law fits into the high wavelength region. So he combined these two laws and gave a new equation which reduces to these two laws at low and high wavelength region respectively. So what he gave is an equation is this one. So Wien's law explains low wavelength region, Rayleigh-Jeans law explains high wavelength region. So he said that okay, we combine these two, and the combined laws which he gave is this one. Is this one. Is this law. E lambda is equal to A divided by lambda raised to the power 5 exponential B divided by lambda T minus 1. So he used these two constants. It's the two constants which he used was A and B. So A and B were the two constants in Planck's law. And you see what does this law, which is E lambda is equal to sorry. Okay. So this was the law. And you look at the at low wavelength, what will happen? At low wavelength, this exponential term will be B divided by lambda T will be very high. And if exponential B divided by lambda T is very high, then you can neglect minus 1. And so this we can write as exponential B divided by lambda T minus 1. We can write as neglecting minus 1 A into A exponential B divided by lambda T. And if you write it like this one, what do you get? You get E lambda is equal to A divided by lambda 5 exponential minus B divided by lambda T. And this was actually Wien's law. So what Planck did is that he gave an equation which reduces to Wien's law at low wavelength. And what happens when we go for higher wavelength, longer wavelengths? At higher wavelength, B divided by lambda T will have a very small value. Okay, and thus this term can be expanded by this relationship. E exponential x. Exponential x is equal to 1 plus x plus x square divided by 2 plus x cube divided by 3. This is known. This is a mathematical relation which you must know. I said you in that introductory video that the language of quantum mechanics is mathematics. So you need to know some basic mathematics, and rest of the thing I will tell you time to time. Whenever there is a mathematics, I will give you the relationship also, so that it could be very easy for you to understand the principles of quantum mechanics applied to chemistry. Okay, so if you use this one, then what do you get? This becomes You restrict yourself to for the first term and you get this one. So this 1 and 1 will go and you will have this relationship. This relationship I have already written here. Okay. So you get this one. And for that matter, this is this relationship, and again you see, this is important, that your energy becomes inversely proportional to fourth power of the wavelength. Okay. And you know this was the Rayleigh-Jeans law. So Planck's did nothing, but he combined two equations, Wien's law and Rayleigh-Jeans. We will not talk about the derivations of Wien's law and Rayleigh-Jeans law. Those who are in physics can do this, or those who are interested can look at any physics book they will give you. I just wanted to tell you that what was the issue with the black body radiation which led to quantum mechanics. So we are not going to the derivation of those equations. I am just using the final equation in order to tell you that what was the issue in classical mechanics which led to the development of quantum mechanics. Okay. So that's why we are not talking about those derivations. So this particular equation given by Planck's resulted into Wien's law at low wavelength and Rayleigh-Jeans law at high wavelength. Okay. So but the issue was here that Planck's used two constants A and B. And so what were these constants? And by manipulating the value of these constants, Planck was able to fit the curve, this equation, into the black body radiation curve. So in order to find the value of A and B, Planck made two bold hypotheses, and this was the birth of quantum mechanics. This he did before the German Physical Society on 14 December 1900, and on 14 December 1900 he made these two bold hypotheses, and he said that energy of radiation emitted from the black body is quantized. Means energy is quantized means energy is discrete, energy is discontinuous. Discreteness means there is a gap, it is not continuous. Okay. So this we say discreteness, discontinuity or quantization all are same thing, all are synonym. Okay. So till that time it was supposed that energy is proportional to intensity and it flows in a continuous fashion in any radiation or anywhere. Okay. So this was a very bold assumption having no theoretical basis. So he made a bold assumptions that energy of radiation emitted is quantized, and then he said that energy is proportional to the frequency, not the intensity. And he gave an equation E is equal to h nu. And this led to a universal constant, Planck's constant, which was a value of 6.62 into 10 to the power minus 34 joule second, as all of you know this. Okay. So using this equation, you know that energy is equal to h nu, or nu is equal to c divided by lambda. So for any wave, so this you can write as energy is equal to hc by lambda. Okay. So using this velocity of electromagnetic radiation, using the wavelength, using the frequency, and using the h value, Planck's constant, he said that A becomes equal to 8 pi hc, and so B becomes equal to hc divided by lambda. Okay, because it was B divided by, it was B divided by lambda t. So lambda t is already there. Lambda t is already there, so hc divided by k. So A becomes equal to, and B becomes equal to, and you know all are constant. All are constant. 8 is constant, pi is constant, h is constant, velocity of electromagnetic radiation is constant. Here also you see h is constant, c is constant, k is constant. K is Boltzmann constant. So in order to find the value of A and B, he proposed these two bold hypotheses before the German Physical Society on 14 December 1900. And he was so sure about it that when he went back to his home, he said to his son that today I have discovered something which is as important as that of Newton. And his words proved prophetic, and this gave the rise of quantum mechanics the birth of quantization was 14 December 1900. Okay. If you look at this equation, which is called Planck's radiation law, this equation, Planck's radiation law, then you can derive the Wien's law from Planck's radiation law. So it is E lambda is equal to 8 pi hc, lambda is equal to 5, exponential hc divided by lambda kt is equal to -1. Okay. So we can derive Wien's law from this one. At low wavelength, what will happen? Hc divided by exponential hc divided by lambda kt will be very high as compared to 1. So you can do the approximations, and then this will be equal to 8 pi hc divided by lambda 5 exponential minus hc divided by lambda kt. Okay. So this you get. And for maxima, what you need to differentiate this equation, and with respect to lambda and equate it to 0. So what you do is that if you differentiate this equation in the next slide, if you differentiate this with respect to lambda and equate it to 0, you see what is the differential? 8 pi hc is a constant. So differential d divided by d lambda, and what you have to differentiate is lambda raised to the power -5 exponential minus hc divided by lambda kt. So you have two terms to differentiate. One is this one, and another is this one. For those of you who have not done much of mathematics, I will tell you. So differential of this term will be this part. If you differentiate with respect to lambda, you get this one, and this you keep constant here. You have first term, you have second term. So this is the first term differential, keeping the second constant, and then you keep the first constant and differentiate the second one, exponential term. So you get, so differentiating the second one gives you hc divided by lambda square kt exponential minus hc divided by lambda kt is equal to 0. Okay. And if you bring these outside as a common factor, okay, then you have 8 pi hc here, and then -5 lambda is equal to -6 plus lambda is equal to -5 hc divided by lambda square kt within the bracket. Okay, because exponential minus hc divided by lambda kt is a constant. Okay. Now in order for this equation to be equal to 0, we can say that the terms in the bracket can be equal to 0. And if you do this one and rearrange, what do you get is this one. Lambda t is a constant. Therefore, lambda max into t is a constant, and this is what is Wien's law. Okay. So Wien's law you can derive from the Planck's radiation law simply by differentiating the equation with respect to lambda and equating it to 0. You get lambda max value, or lambda max t is equal to constant is the Wien's law. So in the most easiest term. Okay. So that we have derived. Okay. Now we can also get the Stefan-Boltzmann law from the Planck's radiation law, and for this you need to integrate. You need to integrate from 0 to infinity E lambda d lambda. E lambda, you know, we have a Planck's radiation law, 8 pi hc divided by lambda is equal to 5 exponential hc divided by lambda kt -1. Okay. So if you put these values, you can get the Stefan-Boltzmann radiation law, and I am leaving this task for you as a home assignment. Okay. You do it as a home assignments. You do the integration, and at the end of this class, I will tell you how to do this. Okay. Then this was the explanation for blackbody radiation. So Planck was able to explain the intensity versus wavelength curve of blackbody radiation using the Wien's law and Rayleigh-Jeans law. Okay. But in order to do this, he made the assumptions, or he proposed the hypothesis which was not having any theoretical basis. So what happened that when a hypothesis comes into picture, the hypothesis is tested time and again with different issues, and when it is observed that it is valid for many different cases, then it becomes acceptable, otherwise it is not. So the same thing happened with this hypothesis of quantization also, and many different issues which was there which was known at that time but was not explained properly, was tried to be explained through this hypothesis.